Hello, am I audible?
Yes, sir. You are audible, sir.
Yes, that's true.
Yeah. Okay. Is my screen visible?
Yes, sir.
Okay. So, so I've added this uh, collab corresponding to SVM to the same folder tiny.cc/mlt_workshop. So you'll be able to find that collab in the day 4 folder. Okay. So those who are interested in coding along with me can open that. Keep that open basically. All right, so we'll get started. So we have seen PCA on day 1 towards the end, right towards the end, and then we saw regression and I think kernel regression on day 2, and then clustering perceptron on day 3, and finally we'll close it with SVM, right? So that will be the last algorithm for this workshop. So just to jog our memories and make sure that we remember what it is that we are trying to solve, I'll very briefly look at the theoretical aspects of the problem and make sure we understand what we are actually trying to optimize here. Okay, so what we'll do is we'll code two things, hard margin SVM and the soft margin SVM, right? So we'll do both. And then if time permits, if we have some time, I'll go back to certain things that I missed out telling on day 1. So a small bit, I just want to cover that. And then there are some closing remarks and we'll close. Okay, so this should be day 4, day 3. Okay, so some of you, at least those who are present during the live sessions of last term or have already attended this workshop last time, will know the set of slides. So I'm just going to rush through them because it's most of it is not really relevant, right? You just need a particular equation that you need to remember for us to go through this collab, right? So yesterday we saw perceptrons, and that works for linearly separable data, right? So with gamma margin. Of course, there are many different classifiers that you can come up with in the case of perceptrons, right? All that we know is that whatever hyperplane separating boundary that perceptron gives you is a valid boundary. That's all we know, right? We don't know if it is the best boundary or not. And we also need to first define what we mean by a good boundary, right? So that is the problem facing us. And as you all should remember, the notion of best is made precise by this idea of margin, right? The margin is nothing but distance of the closest point to the separating boundary, right? And that is the margin. And we are really interested in finding out those hyperplanes which have a large margin. The reason being small margins do not generalize well to unseen data points. Larger the margin, better the generalization. So generalization is what we are looking for in supervised learning, right? So you have a training data set, you train your model and you get some performance on the training data set, but ultimately what matters is that your model performs well on new data points that are presented to you. So that is the goal of supervised ML, right? So maximizing the margin is what matters to us. So the margin, I'll just skip all this, right? So the margin, if you recall, is nothing but 1 divided by the norm of the weight vector, and that is the thing that we want to maximize and subject to some constraints. So all the data points should lie beyond the margin or beyond the supporting hyperplanes that lie on either side of the decision boundary. So that is the constraint. So if you put them together, you get what is called a max margin classifier, or you just play around with the objective function, change the maximization to minimization, you end up with minimizing the squared norm of W subject to these constraints, right? This is the problem facing us. You have to solve this optimization problem. And as you recall, you should recall that this primal problem that we have here, this is called the primal problem. And if you do some math, you will end up with what is called the dual problem. The dual problem is what is there on the right. Well, not yet, but you will see the exact form of the dual problem coming up. So I'm skipping all this. It's like not necessary for us to understand how the derivation happens for solving this column, right? So I'm skipping all this. What you need to remember, however, is this formulation of the dual problem, right? So we are trying to maximize alpha transpose 1 minus alpha transpose some q matrix times alpha divided by 2. So we are trying to maximize this. And if we are able to maximize this somehow, we'll get our alphas, right? And we are going to solve for alphas. This is what we are going to do today. How do we formulate this in NumPy? And once we have formulated this, how do we solve in using SciPy, right? So we will be seeing one more library today, a small bit of SciPy. So that is the agenda. So you need to understand how we are going to solve this part. You don't really need to understand how we get here. I am assuming that you have done this during the theory leg of the course, right? So, but please make it a point to remember this particular equation, because this is what we'll be trying to solve, this optimization problem. Okay, so again, what are support vectors? Support vectors are those data points for which the alphas, the optimal alpha values, right? Once you solve this optimization problem, you will get some alpha values, right? So they should be greater than 0 for the support vectors, or the other way around. So those points for which alpha star is positive is a support vector, right? And you all already know that every support vector should lie on the bounding planes, right? And they should, just because a point lies on a bounding plane, it need not be a support vector. All these things we already have seen it in great detail. So I think this is what kind of summarizes what we'll be doing today. Any questions? Okay, so you'll be given, you'll see a data set like this, a toy data set like this, and then out comes an alpha star. So what we are going to do today is open this black box. Okay, to some extent, you won't be able to do it completely, but we'll try to open this black box and see what is there inside it. Okay, so how does this data set go into this black box and get transformed into these alpha stars? Okay, so that is the thing that we'll be doing today. Okay, so shall we get started with the code? Any questions about this theories part so far?
Just one thing, sir.
Yeah.
This coding in the sklearn library, when we are using the calling that library function SVM SVC, is it that inside that this type of coding is present?
Okay, yeah, that's a good point. Not really, not exactly SciPy. They don't use SciPy. They, in fact, SVC, SVM, sklearn.svc uses another popular library. I think it's called liblinear or libsvm, right? It's one of these two. So what this libsvm does is, I don't think it is exactly what we are going to do today, right? So it's much better version of what we are going to do today. So I won't say what we are doing today is wrong, but then what sklearn does is obviously much more optimized, and that's the right way of doing it.
But can I able to see the coding that SVC or means sklearn library is doing?
You're asking if you will be able to see it, or?
No, I'm able to see that.
Yeah, you can go to the Anaconda distribution. If you're using Anaconda, you can download the entire this thing and see the entire code.
Right. So if I am not wrong, sklearn uses another library, libsvm. So you can search for, let's see, libsvm. It's a very popular tool, right? So you can search for this, and internally libsvm is what is being used by sklearn, if I'm not mistaken, but I'm not sure. You have to check it out.
No, you're right, sir. Even logistic regression, it implements something called as liblinear.
Okay.
Right. So I think there's some family of this liblinear, libsvm.
Okay.
I had another question. That see, the moment we move to something which is a little more, let's say, deep learning oriented, we will probably use PyTorch or TensorFlow or one of those things. So, like, are they equivalent stuff of like equivalent of this in those libraries also? I'm guessing there will be, right, sir?
So TensorFlow, PyTorch are, I don't think they have support for classical machine learning algorithms, right? They are mostly neural network based.
Okay, I don't know. I just wanted to check, because if that has everything, then why not just directly learn that rather than?
Right. No, I think PyTorch, TensorFlow, and the whole deep learning stuff. It's all deep learning based, right? So only neural network support will be provided.
Okay. Thank you.
Okay. Right. So we'll get started. So you have a data set that is given to you. Okay. So this is a toy data set, and these are handcrafted, right? So I have they manually chosen the data points. Of course, in a real life setting, you will be given X, or you may have to construct X. Okay, but anyway, either way, you are given X comma Y. Okay, and we'll start with that. So you'll have to train a hard margin SVM for this, right? So this is first a hard margin SVM. So X is of shape D cross N as usual. Let's take a look at the shape of this data set. So I'm going to say that X dot shape, store the features in D and the labels in, the number of data points in N. So you see that there are two features, R2. The problem is in R2, and there are 20 data points. Okay, so this is like the simple part. Now, what we have to do is we have to visualize the data given using the scatter plots. Scatter plot, and +1 goes to is given green color, and -1 is given a red color. Okay, so let's go ahead and do it. What is the command for a scatter plot? You have seen this yesterday, also 2 days before.
plt.scatter.
plt.scatter, right? So let's go ahead and do this. Okay, what do I plot here?
X
0 to all
and
okay, X what?
0.
Okay, X0 colon, right? So this is like feature 1, and for all the rows, all the columns, and this is the second feature. So basically, I am plotting the X values and the Y values, or the X1 values and the X2 values. Is that right?
Yeah.
Okay, so let's plot this and see what we get. They're all blues, right? So we now have to add the label, or rather color them appropriately. So this is how we are going to do this, right? Request you to mute. Someone is not on mute, right? Okay, so this is how we are going to color the scatter plot, or the points in the scatter plot. So we create a color array, right? So this is a color array where the zeroth element of this array is going to be red, right? And the first element is going to be green. Okay, so it will become clear in a minute why we are doing this. And the labels are what? The labels are 1 or -1. So what I'm going to do is I'm going to create a new array. I'm going to call it Y color. So wherever Y is double equal to 1, wherever 1 is present in the labels, I'm going to retain this as 1. Okay. And wherever it is not equal to 1, I'm going to make this 0. Okay. So I'm I'm doing this particular transformation, and then what happens is, if I pass Y color into this array color, for every data point, I'll get the corresponding color associated with it. Okay, so let me just run this once, and then let's see what happens. Okay, so I want to know if we have understood what we have done here. Is there anyone who has a problem or a doubt with this?
Can you explain once more, sir?
Okay, see, what we have done is, let me take a simple example of three data points, right? So let's say they have the labels np.array of 1, -1, 1, right? So these are the three data points. So I'll copy this color array. This color array is red, green. Okay. What I want as output is corresponding to each label here. I want either red or green, depending on what the label is, right? So finally, this is what I want the output to be. So green, red, green, right? So this is what we want. This is the desired output. So the way we are doing it is, if I directly pass this array into color, I'll get 1 and -1 as another index, right? I don't want -1 as one of the indices, because 1 and -1 will both give me green color. Do you agree? Y of color of 1 and color of -1 both correspond to the value green. So I want to make this 1, 0, 1. Okay, so I want to make this 1, 0, 1. The way I do it is, wherever you have a 1 in your original array, make 1, keep it 1, don't do anything with it. If it is not 1, make it 0. So now if you run this and see, you will note that this has become, this ones have been retained. Wherever you have a -1, that has become 0. Okay.
What's the purpose of renaming -1 to 0?
See, the reason I am doing this is, I want to index them using this. So in fact, okay, maybe let me see if I can directly do it this way. That may make things simpler. Does this work? Okay, this works. So what we'll do is, let's skip this part. I'll simplify this. In fact, you don't even need this. You don't even need this. Okay, so wherever it is 1, make it green, make the color green. Otherwise, make the color red. Okay, let's see if this works. Okay.
Color,
Okay.
not color, it's giving the syntax like tag. It's
Okay.
not point.
Yeah.
String element.
Right. So do you get it now? What I have simplified it. You can ignore the what I did before. So wherever y is double equal to 1, you give it a green color. If not, you give the data point a red color. So if you actually visualize Y color now, if you look at Y color, it'll actually be green, 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 so on, and then red, red, red.
Could you show the original data, X?
Yeah. Okay, so they're all greens, and then you have all reds. This is a why are we seeing some of them as, why are we seeing the last two as green? Something that I'm not sure. Once again, let me just print both of them and see. Okay. Why is the last two here 1, whereas the last two here is not 1? Okay, for some reason there was some issue. I don't know what. Okay, do you now see this? The first 10 data points are greens, the last 10 data points are reds. So what I have essentially done is I have transformed the labels into colors, and I used np.var, this particular method, to convert labels into colors. Is that clear now? Is that clear to everyone? Is there anyone still having a question with respect to this particular piece of code? Okay, I hope it is clear. So I'm moving on. Okay, so let's now ask this question, right? So here there was a question: is this data set linearly separable? What do you all think?
Yes.
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 Okay, so it seems like it is linearly separable. Okay, so visually at least there seems to be a line that kind of goes here. So before we move on, let's make it a little more precise by adding our axis here so that we have some idea of what it looks like. Okay, so yeah, so this is how it looks like. Let's also do the following. I don't want them to be I don't want these to be solid lines. So let me change. I think this is line style. And let me try this. I'm not too sure. Okay. Okay, so we are changing the line style instead of having a solid line to differentiate. So we'll use the solid line for the decision boundary, right? So let's use a dotted line. And this seems to be a little too strong for our taste. So what we'll do is we'll change the line width to be something like 0.5. Okay, that will make it thinner. Okay, it's just axis, right? So we don't want it to be too prominent. Okay, so this is what we have done. This is a new change. Okay, so just give me a minute. Do you all know, do you all kind of are able to figure out why this green point is getting added here? Is anyone able to figure that out? I actually don't have a 0, 0 in my data set. But somehow this green data point is getting added. I don't know why. Anyway, if I run it from the beginning, it disappears. We'll come back to that. Okay. So yeah, here's another question. Is there another way to determine if this data set is linearly separable or not? Apart from, say, visually inspecting it, do you all see any other way of determining linear separability?
You can use perceptron.
Okay. All right. So we'll try that. We'll very quickly try that. So let's start with np.zeros of d, right? So d now is what? D is equal to 2, right? So w is initially 0, 0. That is what it is. Okay, so what we are going to do is we are going to loop through the data points. You already done this yesterday, so I'll just quickly go through this. We'll cycle through all the data points one after the other, right? So I'll leave the condition here empty for now. So while the perceptron has not converged, okay, while the perceptron has not converged, what I'll do is I look at the predicted label of this particular data point. So let's say x of I is the data point. X of I into w transpose x. Let me write it as w transpose x, w transpose xi. Okay. So I call this y hat. This is 1 if this is greater than or equal to 0, right? This is 1 if w transpose xi is greater than or equal to 0. Else
You did not
minus.
write transpose.
Actually, we don't need to write. We don't need to write transpose, right? Because
Why?
W is a vector, right? W is a single dimensional vector. Therefore, so let me. So let's say W is 1, 2, and X will also be a one-dimensional vector. So if you do W transpose X, you will get 11, which is the dot product. You can also do W transpose X,
Okay.
but it doesn't make any difference. That's because when you have a single dimensional array, W transpose and W is the same thing. There is no concept of transpose for a single dimensional array that will work out. Okay, so yeah, so this is y hat is what? The predicted label of the ith data point. So if W transpose Xi, I'll say W transpose Xi, but I am not adding the transpose. So that should be, it's implicit in what we are doing, right? So W transpose Xi is greater than or equal to 1, then y hat is 1. If not, it is minus 1, right? So we have now predicted the label of Xi. Now we want to know if it's a mistake or not, right? So what do we do for that? What condition should we check?
Whether y hat and y are the same.
Yeah, so whether y hat is equal to or not equal to y of I, right? Y of I is the label, true label of the ith data point. So if it is not equal, then we have made a mistake. So what should be the update now?
W plus XY.
Okay, W plus equal to X of I. Okay, so here notice that each column is a data point, right? So the ith column, that is this, into the true label. So this is the update, right? So you have made an update. Okay, so whenever you make a mistake, what you are going to do is that you are going to start cycling or cycling through the data points all over again. Okay, so keep that in mind. If it is not a mistake, then I'll update something called correct, right? So there's a variable that is used to keep track of how many data points I get correct. So I'll update correct to be, I'll increment correct, right? So if it is not a mistake. However, if I make a mistake, I will set correct equal to 0 because I have to start all over again, right? So I have to reset my counter so that next time, until the next mistake, I'll keep incrementing correct. Okay, you will see why this is useful in a bit. Okay, you have done.
Hi, excuse me.
Yeah.
Just while doing this update, we are doing W plus equals to X colon comma I. Why is that colon comma I? Because we want just the ith column, right? So
yeah.
So why the colon? Because earlier when we were doing this y hat, then we did not do this colon thing.
Yeah, that's because y hat is a vector, right? I mean, y of I, you mean? You mean y of I or y hat? So you're asking why is it y of I and not y colon of I? Is that the question?
No. In the very next step, why is it x colon comma I?
Yeah, that's because so this is x, right? X is okay. It's like bad to look at it this way. Let's see if we can get a better picture here. Okay, this is x, right? So each column is a data point, right? Yeah. So if I want to take the say 0, 1, 2, 3, 4, fifth data point, right? This -1, -6. What do? I take all the rows, but I fix column 5. Right? So that is -1, -6.
Got it.
Okay, so that is how we take, that's why we take x colon comma I.
Hello, sir.
Yeah.
So y hat formula is W transpose X when we solve the problem, but here you write only W at the rate Xi. Why? Okay,
so I just explained this, right? So if W is a vector, you actually in NumPy W and W transpose are the same thing. So okay, for convenience I'll add this. It doesn't matter, but if W is a vector, a NumPy vector, meaning a one-dimensional array, W and W transpose are the same thing.
So what is that syntax while less than and greater than? How is that working?
This one?
Yeah, no, line number 4. While less.
No, yeah, I am not complete. I am not completed, right? So this is add termination criteria condition, right? So add termination condition, I'll add it. So this should also be, by the way, this should also be.
Okay, I thought like there was an output array 0,0, so I thought like how's that working?
No. This is something we'll add now, right?
Okay. Yeah.
Okay, so this is what we do. So while the termination condition or while convergence has not been reached, you go through all the data points, and if it's a mistake, then you make an update and you reset this correct counter. If not, you know that you have classified 1 point correctly, so increment this. Now you have to make a small check here, right? So if I is doubly equal to n, right? If you have reached the last data point, what do? It's a while loop. Remember, it's a while loop. So if you reach the last data point, what should you do?
Break.
Loop through again.
Okay, if I have to loop through again, what do I need to make? What change do I need to make for I, the variable I?
I should again be set to 0.
It should be 0.
Right. So you reset the value of I. So you're looping through. It's not a for loop, right? So there's no loop variable that is explicitly being specified, like for I in range of n. No, that's not there. So you have to make sure that I becomes 0 once I reaches n. Otherwise, you'll have an index error, right? You'll be trying to look for some element which is not there in your array, right? So you have to do this, and
it then shouldn't we also have something like I plus plus so that I gets incremented?
Right. You're right. So before that, you'll have to do an I plus equal to 1 because you have seen one data point. So you have to move to the next data point. Okay, so
sir, one small doubt.
Yeah.
Sir, if the epoch has some six corrects comes, sir, continuously.
Okay.
And after that, the seventh thing is wrong. Then you are saying like you will reset the correct to 0. So
yes.
So it should actually keep count of that 6 corrects. So how resetting to 0? So you have to fix that particular thing.
No. Right. So no, I'm resetting to 0 for a reason. So when do you know that your algorithm has actually converged? When does perceptron converge?
All data points are correctly classified.
Okay, when there are no mistakes, right? And when there are no mistakes, what can you say about correct?
Correct equals in.
Sorry, I didn't hear that.
Correct equals in.
Correct, right? So when you have no mistakes, that means you have consecutively updated the variable correct n times, right? For each of the n data points, you have not found any mistake. So when correct is not equal to n, or rather, keep looping as long as correct is not equal to n. The moment you make n correct answers, right? The moment you have n correct answers, it means that your algorithm has converged, so you'll exit out of the loop. Okay, do you all get the logic of what we have done?
Sir, but here we are not resetting the correct. I think we should reset the correct also, right?
We are doing that, right? So correct is being reset to 0 whenever you make a mistake.
Yeah. Okay.
Okay, so let's run this and see if we are getting anywhere.
One more doubt, sir. I have.
Yeah.
Like if the algorithm is not converging for a given data set, then the correct thing will again goes to 0 and the while loop will never end, right?
Correct. Yeah. For a data set that's not linearly separable, you will never converge. So this is not really a good way to find determine linear separability, right? So this is not the best way. But here this is just a toy problem, so we are trying this out. Okay, so notice that it has converged.
I have one question. Sorry, maybe I'm wrong here.
Right.
When we are learning this particular algorithm, rather SVM, and we're learning and we're looking at this, we go through each data point, and once there is a mistake, we correct that with the addition of WX, and we continue further. We do not go back. I remember.
We don't go back, right? We continue.
Here, when we say correct is equal to 0, when it is not, we are going back.
Okay, so we are actually moving, right? We are always moving forward to the next data point. So we are going back only on. So we are only resetting a particular variable to make sure that it gives us the correct criterion for convergence. That's the only thing we are doing. Right? In fact, we are moving on. Always we are moving on.
Yeah. Okay. So in the session one, we were actually talking about, I'm talking about the MLT course itself. We were saying 1, 2, 3, 4, 5, 6. 6 is a mistake. We correct the 6 and go to 7. But here we are saying 6 is a mistake. We're going back to 1.
No, right? So see, 6 is a mistake. So let me just print this out. We have a mistake at data point I plus 1, right? Is actually I plus 1 because we start indexing from 0.
Yes, yes.
Right.
Okay.
So we have a mistake at I plus 1. And I'll also print the following, right? So I'll print it here, right, at the beginning. So we print the following thing. We have a mistake. We don't have a mistake here. We don't know. We are looking at data point I plus 1, right? Here also it's, so if I run this now.
First time we enter loop where it is.
See, this is what happens. We are looking at data point 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then the 11th data point happens to be a mistake, right?
Correct.
And then what we are doing is we are looking at data point 12. Okay, so we keep doing this. Only after we reach the 20th data point do we cycle back. Okay, after we make a mistake, we go to the next data. Only the value of correct is what we are resetting.
Resetting. Okay.
Okay, so
okay, the I is still going on as a count.
Right.
Okay,
Yeah.
fine.
Yeah.
Sorry. That was my mistake. I misunderstood as correct being same as I.
Yeah. Right. Move to the next data point. So this is what if you are at the.
Karthik sir, sorry, we don't have to discuss this, but even if we didn't do that, theoretically we went back to the first data point. As long as we cycle through one epoch without any mistake, it's good enough to say that it will converge, right? So it doesn't matter, right? You have to just start with the next data point. Theoretically, it doesn't matter. Shouldn't.
You are right on that one. That is what I wanted to get clarified actually.
I think it's just a process. It's easier if we follow that process, but I don't think it matters if we reset it to 1 and start cycling through the first one all over again, because eventually all data points have to be classified correctly one way or correctly.
Right.
So
Yeah.
we have to basically run through one pass without any mistake.
Right.
Not in the
Also,
middle
I'm
or
guessing.
I plus 1, or it doesn't matter according to me, but it may just be a good thing to follow this order. That's all.
Right. Yeah.
Also, I'm guessing it is down to actually a large set of data. If there are a million points, you start going again to 1 every time. Maybe that is where.
So it's inefficient. Yeah. So those things are there, Ravi. You're right. So it's programmatically it could be inefficient, but but theoretically,
logic-wise, it doesn't make much
it's
difference.
the same thing. Essentially, you have to classify all points correctly.
Yeah. Thank you. That's all it was. Sorry to interrupt.
No, sir, I'm not getting this because unless
just ignore it. It doesn't matter. It doesn't matter. Just whatever Karthik sir said is correct.
Clarify. If I don't go to the complete epoch, then my weight it's not getting updated now, considering all points.
Okay, so see, strictly speaking, the algorithm is what the algorithm states is that pick up a mistake and then use that mistake to update the weight vector. That's what the algorithm says, right?
So if you do this, means say there is 100 data points and you find a mistake at the second data point, instead of going forward, you are coming back to 1. But there is a possibility if you do this, you will just flip-flop between a certain data point and you will never reach to this 100 data point.
See, I also had that doubt initially, but it won't happen.
That won't happen. You have to go through all of them. You will go through all of them.
Right? Because a subset of assuming that your argument is correct, let's say you get stuck, there are 50 data points, assuming you get stuck at the 10th, somewhere in the first 10 data points, you get stuck, right? But that will never happen, right? Because the first 10 data points are also linearly separable. So eventually, even if you cycle through 1 to 10 repeatedly, you will have to classify those 10 correctly, right? So your mistake will lie beyond the 10th data point only. So you will have to go to something beyond 10.
But sir, The question is,
yeah.
when
So
you
what? Okay, we'll do the following, right? We will discuss the convergence part at the end. We'll go through a few more cells and get back. Okay, so we'll just go through a few more cells and then we'll get back to this. So this is a slightly theoretical point. We'll get back to it a little later. So what I'll do now is I just want us to do the following, where we'll visualize what this looks like, that decision boundary. Again, you have done this yesterday, but the code that we write now will get reused eventually. So what I'm going to do is, this is going to be, this is in the range -5 to 5, right? So I'm going to define a partition of the x-axis as -5 to 5. Okay, and W vector is actually what? It's two-dimensional, right? So W transpose X will be W naught X plus W1 X2 equal to 0, right? This is the W transpose X decision boundary equation. So if I want to write X2 in terms of X1, it will be what? It will be minus W naught X1 by W1. Do you all agree? This will be the equation of the line of the decision boundary. Is that okay with all of you? X2 is minus W0 by W1 X1. So let's go ahead and plot this. XDB, right? XDB is basically this X1, and this is minus W0 over W1 XDB. Right? I don't want to use X because it will again confuse us. So I'm using XDB. Now let's make it a black color decision boundary. Okay.
I'm sorry, I don't understand the 6th and the 7th line.
Okay, so this is W. Do you get this part? W transpose X equal to 0, right? That is the equation of the boundary.
Yes.
So W0 into X1 plus W1 into X2 equal to 0. That is what it is.
Right.
Right. So what I want is, I actually want, this is the equation of a straight line, right? In fact, since it's 2D, I want to plot the decision boundary as y versus x, right? As it's a straight line, so its equation is y equal to mx in this case. So I'm finding the value of m actually. So if the decision boundary is y equal to mx, what is the value of m? The value of m turns out to be minus W0 by W1. Okay, this is what I have done. So it's like you can think of it this as y equal to mx, where I have computed m using the W. That's all I've done. Okay, again this row point is coming. I don't know why it keeps on coming. Just give me a second. I'll remove these two prints and I'll get back to that line. Okay, so is this part now clear? What we have done? Where have we done this? Yeah. So I see I've just plotted y equal to mx. M is minus W0 by W1. Now we can also, like what we did yesterday, we can plot one arrow starting from 0, 0 to W0 and W1. Okay, that will be the vector. So I'll just give some parameters. Queer is one way to do it. This is another way to do it. You can choose either one. Okay, so if you plot this, you get something like this. Okay, now I have a question for all of you, sir. Right, so this doesn't seem to be perpendicular to the boundary at all. So have we made some mistake? Correct, right? So our graph is not correctly scaled. So this is -5 to 15 and this is -15 to 15, right? So these are small things, but they may actually throw you off. So we have to scale our graph. One way to do it here is, what I'll do is I'll make sure that the limits, the x-axis and the y-axis, the limits of the graph are identical. So I'll make it minus 15 to 15 in both the cases. Okay, so
Sir, how do you set the decision boundary at minus 5, 5?
sorry, where? Decision boundary?
In line number 5.
Line number. Okay, so it's just the X range, right? I just want something to cover the whole thing, right? So here I came up with that minus 5 to 5 based on this, right? The horizontal axis ranges from minus 5 to 5. So all the data points are lying within that region. So I just need to plot a line that will cover this stretch. That's why I use minus 5 to 5. Okay, I mean, you can use anything. You can use minus 15 to 15. It really doesn't matter. Okay, so did everyone get what we have done here? Any questions so far?
No, sir.
Okay. So we move on. Now we finally come to the SVM part, right? So compute the objective y that appears in the dual problem. So in the dual problem, where is the dual problem? The dual problem is here. So what is the y? How do we write it using NumPy? This is y. What is it? Can someone?
np.i.
Right. So np dot tag of y. Right. Y, remember, they are the labels. There are 20 labels or n labels. Okay, let's look at y dot shape, and we'll also look at what y actually is. Okay, so this is a 20 cross 20 diagonal n cross n basically, right? So this will be n cross n diagonal matrix, and first 10 diagonal elements are ones, next 10 diagonal elements are minus 1. Okay, so we have found out capital Y. So now alpha is the dual variable, and the dual objective is of this form. Okay, so we have to compute this matrix Q. So let me go to the equation. So what is the matrix Q here? How do we write it down?
Y transpose X transpose XY.
Okay, right. So it's like the beauty of NumPy is you can exactly write it down as though you were writing some math equation. So it is Y transpose X transpose X Y. Okay, this actually gives you Q. Okay, so we have made some mistake. Wait, what is that mistake?
Sir, has Y been converted to a matrix?
Yeah. So see, the problem is there is okay, now I understand why that extra data point was being printed. So there is this control F9 that I'm running. So for those of you who are not aware of this, there is a command, there's a way to run all the cells in your collab. That's called that's control F9. Okay, so it will run the entire cell, every single cell in your collab. So what I have is in the soft margin SVM, I have a data point that is 0, 0. So this X gets overwritten. Okay, so it's like that's why it's better to run control F8. Anyway, so that doesn't matter, but let's visualize Q or like print out Q and see what happens. Okay, it looks a bit nasty. So rather than seeing what Q is, it's enough if we look at what the shape of Q is. Okay, it's 20 cross 20. So any questions in steps 1 and 2, what we have done, how we got capital Y or how we got Q?
What was the shape of X?
X is 2 cross 20, right? X is what? 2 cross
20. So Q is n by n.
Yeah, Q is n by n. Q is n, yeah. This is n cross n, n cross d, d cross n cross n again. Okay, so Q is n cross n again. Okay, so that is step 2. Now, step 3 is what? Step 3 is about computing the objective function. So this is the objective function. We have to maximize something subject to some constraints, right? So this is the objective function, and we have to programmatically express that. Okay, so in Python, that's what we have to do. So we will do the following, right? So SciPy, the library which we are going to use to minimize or optimize the function, it works with functions that you are trying to minimize, right? So we'll try to call a minimization routine. So it's easier to work with the negative of the objective function, right? So this is the original objective. Okay, recall this is the original objective, alpha transpose 1 minus alpha transpose q alpha by 2. So if we are trying to maximize this, okay, but SciPy is it's easier to minimize. Therefore, we are going to minimize the negative of this. Okay, the negative of this is nothing but alpha transpose q alpha minus alpha transpose. Okay, do you all get this part? We have just done a multiplication by -1. Okay, so now we'll go ahead and write down this function. So f, the objective function, is itself a function of alpha. Okay, that is itself a function of alpha. Now, what is that? It is half into, okay, notice how easy it is to transform math to NumPy, alpha transpose q alpha minus alpha transpose. So you can, ones is nothing but a vector of ones, right? So I can write this down as np dot ones of, what value should I plug in here?
20.
Okay. Yeah, it's actually 20, but in terms of the variables, in terms of the variables, what variable is it?
X dot shape 1.
Correct. X dot shape 1. Yeah, or n, right? N. Okay, so you could write it down like this. Or alternatively, something that's simpler is, what is this actually? Alpha transpose 1 is what? Mathematically, what is that? Alpha transpose 1.
A summation of alpha elements.
Correct, right? It's just the summation. So I can just replace this with alpha dot sum of. Okay, that will just sum the vector. Okay, so if it's not clear, like just, let's take an example, a very quick example. Alpha, let's say, is equal to, in this case, 1, 2, 3, 4, 5, and 1's equal to np dot ones of 5. Okay, assume there are only 5 data points. So if I do alpha transpose ones, I'll get 15, right? 15 is what? It's the same as alpha dot sum of. Okay, both are the same thing. So what we are going to do is, we are going to use this. Yeah.
Yeah, so just one thing, shouldn't we also pass this q as a parameter to this function?
Okay, actually, it's not needed here because q will remain in the memory, right? As long as you don't initialize q anywhere inside, it will remain. It's like a global. It's not. I mean, I shouldn't use the word global, but the function will be able to access q. It's a list or a NumPy array, right? So it will be able to access it.
Okay, and one more thing, can you just remind us what this alpha was? Was this the vector of all the Lagrange?
Yeah, exactly. So each alpha I is a Lagrange multiplier corresponding to the ith data point.
Okay, got it. Thanks.
Yeah. Okay, so that is the objective function. Objective function, remember, is a function of alpha, right? It's the function of alpha. There is one alpha for each data point, and there are 20 data points, right? So alpha shape will be 20 dimensional, right? It will be a 20-dimensional vector. So will the function return a scalar or a vector?
It should return a scalar.
Yeah. It will return a scalar, right? So recall, this is all, see, alpha transpose 1 is what? Sum of alpha. So that is a scalar. And if you think about this,
Also, we are max. Yeah. So we'll get the maximum of it, right?
yeah.
So that should be a scalar. Yeah, I thought it would return the
Right.
vector of alpha. Sorry, yeah. Okay.
Okay, so this is the objective function. Now, finally, once you have the objective function, you can now go ahead and optimize it. Okay, so we now have a minimization problem. Again, I'm emphasizing this. We have a minimization problem because we have taken the negative of the objective, right? So that's why we have the minimization problem. So in SciPy, there is a module called optimize. Okay, there is a module called optimize. So optimize has a method called minimize, and minimize accepts the objective function that you want to minimize. Okay, and it will use one of the optimization techniques that is something we don't need to know. It has several techniques up its sleeve, so it will use one of them. All that we need to give it is an initial vector. Okay, an initial vector. So we can conveniently choose this as a vector of zeros, okay, of size n. Okay, remember alpha is n dimensional, so it has size n. Okay, you give the objective function that you want to minimize and you give it the initial vector that you start with. So it's an iterative algorithm. Whatever algorithm it uses to minimize is going to be iterative in nature. Okay, that's why you give it an initial starting point. Okay, starting point, and that is a vector of zeros. If you just stop here, there's a problem. So what problem do you think this poses? If you just stop here,
That will be unconstrained.
correct, right? It will be unconstrained. So we need a constraint. Okay, so we need a constraint. Thankfully, SciPy provides that also. So optimize has several ways of defining constraint, but here the constraint that is available to us is in the form of a bound. Okay, the constraint is in the form of a bound, meaning the alphas are bounded. So there is a lower limit, and there is an upper limit for alphas. Okay, so as you see, bounds constraint on the variables, the constraint has this form. Lower bound less than or equal to the variable you're optimizing for. In this case, it's alpha, not x for us. And there is an upper bound. So what will be the lower bound? What will be the upper bound? Alpha is bounded below and above by
zero.
Okay, lower bound is zero. Okay, what will be the upper bound? Infinity, right? So it's not bounded above. Actually, strictly speaking, it's not bounded above, but a way to express that in NumPy is you give np.inf, right? So np.inf, by the way, is, and just type this and we'll see. Okay, it is infinity, right? That's one of the valid tokens in NumPy. I have not tried this, but let's see what happens. Okay, so this is expected behavior of your symbol infinity, right? You add, you scale, okay, it remains infinity. Okay, so of course, if you scale it by -2, then you get minus infinity as expected, but you can do other things also. You can verify if it is truly infinity. Okay, so you can try things like this. Okay, that is also less than np.infinity, right? So this is what we want, right? So the lower bound is 0, upper bound is infinity. Okay, now we have all the ingredients for a constraint optimization.
Question.
Yeah.
This SciPy is using the alpha init, which we've initiated to zeros. So does it automatically update those alphas till we reach the minimum?
Exactly. Yeah. Internally,
how does it do so?
Okay, there are several algorithms. So if you look at, there are several techniques, right? So I'm not aware of all the techniques, but if you look at optimize.minimize, optimize. We copied it incorrectly. Okay. Okay, 1 second. Let me just run this first and see if it works. Oh, okay, I'm missing something.
Sir, one question. How does the function know it has to minimize with regards to what parameter?
That it knows, right? Because you have passed f. Yeah, once again, I'll get back to your question. I just want to know what I'm missing. Making a type error. Make sure that this is scalar. So it's saying that this is not a scalar. Okay, let's go back to f of alpha. 0.5 into alpha transpose q alpha. Seems correct. Q seems correct. Y transpose X transpose XY. Okay, just give me a minute. I'll just try out some value of alpha and see what I get. Let's say alpha is np.0, so n. Okay, this is 9. Okay, so f is a scalar. That seems to be correct. Is anyone able to see what the error could be?
Sir, actually, I think it is maybe considering the two options as the parameter for alpha.
Right.
Takes
You are right.
one position argument, but two.
Correct. You are correct, right? This actually should be bounds equal to, right? You are correct. So this is actually a keyword argument. It's not a positional argument. So that's why we are getting that error. Right. So yeah, let's go back. Now there were two questions, right? One is how does it know how does the optimization work? See, the optimization works in an iterative manner, right? So just like we have gradient descent, there are some other higher order optimization methods. And let me go take you to that page, scipy.optimize. Okay, so SciPy has this particular, there is minimize. So this is minimize, right? So this is the function that we're actually using. SciPy.optimize.minimize. You take the function as input, some initial value, and for us, this is the one which matters, right? Now there are several methods. So for example, these are all names of the methods, and I don't even know what these are. These are all mostly higher order optimization methods. For example, have you all come across this Newton-Raphson method? It's a second order method for finding an optimal point, right? So these are all different algorithms that SciPy uses to converge to the to an optimal solution, right? So
sir, Newton-Raphson method is used to find the roots.
Roots, correct. Yeah, that's a root finding algorithm. But there is another version of, okay, there is an algorithm that goes by the same name of Newton's method. Okay?
Yes.
So the Newton's method is used, it uses a second order approach to find the optimum solution for a problem. It uses the Hessian, if you all, some of you know what the Hessian is, it uses Hessian to arrive at anyway, right? So this is how it works. So you don't need to know exactly how it works. It is using one of these iterative optimizing algorithms and arrives at the answer.
Third, that method is also used to find solutions to differential equations and all that.
Okay.
Second order different finite differences.
Right.
That's what memory serves.
Okay, so yeah, so what was the other question? The other question was, how do I know?
I was asking, like, how does it know with respect to which parameter it will?
Okay, so this f has this alpha, right? So it, if I'm not wrong, it implicitly makes use of this alpha, right? It knows that it's minimizing with respect to
whatever is the argument of the function.
Right.
Okay,
so if you look at the output returned by this algorithm, let's look at the result. I'll call this the result of the optimization problem. Okay, and let's see what all is there in the result. First thing is that there is one success message, right? It says that the algorithm has converged. Okay, so that is one thing. This gives you the value of the value of the objective function at convergence, right? It's -5 in this case. It also gives you the optimum, the argument, right? In this case, it's the argument, the argument at which the function reaches its minimum value, right? That is x. Okay, it calls it x, for us it's alpha. So you don't need to know what these things are, they are not relevant. So if you notice this Hess inverse, this Hessian inverse, so apparently it has used some second order method to converge, but all that is irrelevant for us. What we need is the optimal alpha, and as long as someone provides us that, we are good. Okay, so these are the alphas. Okay, these are the alphas. Notice that there are 20 such values. And what can you say about these values?
These are the support vectors.
Right. So these are the alphas corresponding to the support vector. So we have found the alphas. That's what is most important. So the next step is
Sorry,
yeah.
can I just take you back?
Yeah.
I lost my. I'm not able to stand line number 5.
Yeah. Okay. So there is this. When you actually solve the optimization problem, it will return a result. So it will return a result object. Okay. And I'm calling it RES. So the result object will have several things. It will have a success message, whether it converged or not, what algorithm was used, what is the value of the objective function at the optimal point. And among all these things, it will also have what is the x star, right? Or what is the optimal point or the argmin for this particular problem. The argument at which the function reaches its minimum. And we are interested in that argument. And that is res.x, right? I'm extracting it out. So alpha is actually res.x, result of the optimization dot the argmin. Okay, so basically, if you run these lines of code, right, it will these two put together, the first 3 lines or 4 lines are doing what? They are doing this thing. They are maximizing this expression actually. That's what they are doing. These 4 lines correspond to solving this optimization problem and giving us the alpha star that we are looking for. This alpha star is actually this alpha. Okay, so that's what we have done so far. Okay, so how do we find the support vectors? Now, how do we find the support vectors?
You can check the index.
Okay, so, right. So wherever alpha is greater than 0, those are the support vectors, right? There are 20 alphas. So if you run this code, you will get a binary array, right? An array with binary values. Wherever the value is true, that particular index corresponds to a support vector. So you can do a nice thing here. You can do this advanced indexing, right? So look at those columns for which alpha is greater than 0 and just give me those columns. Okay, I'm sorry, I have to run this whole thing again. Okay, so these 6 points turn out to be our support vectors. So we have extracted those points for which alpha is positive. It is these 6 points. Right, so that is the support vectors. This will become clear when we actually plot it and see. Okay, I'll come to that. So what is the optimal weight vector? Optimal weight vector is W star is sigma alpha I xi yi, but it is also xy alpha, right? It is also xy alpha. So since we are having a matrix form, we can just write down optimal W as x, y, alpha. Okay. So it turns out to be 3, -1. That is the optimal alpha that we have here. So far, is it clear? Any questions? Any questions so far?
So those support vectors are two-dimensional. For instance, one point in that is x is 2 and y is 5. Along the x-axis is 2 and
correct. Yeah, one
along
of
the
them
y-axis is 5.
Yeah,
2 by
yeah.
2, 5. Okay, okay.
Okay, so now we plot the decision boundary. The interesting thing is we can just reuse the code that we use for perceptron and it will work, right? Because W is the only thing we have changed. If you notice, W is the only thing that has changed, and W we have anyway recomputed, right? So we can just reuse the same plot. Okay, so let's just compare these two things. Let's compare the one we have here and the one we had here. It will be slightly difficult to compare because they look more or less similar. Okay, the margin is too small here. Okay, so making a proper comparison may not be possible, but still. So one thing we could do is change the limits so that you get a slightly zoomed in picture of what we have here. Okay, so that is your hard margin SVM. So what else do we need to plot here to complete the whole picture?
Gamma margin.
Okay, the supporting hyperplanes, right, which pass through the or on which the support vectors will lie. So let's go ahead and do that. So this is the decision boundary, right? This is the decision boundary that we have plotted. Here, what are we plotting? The weight vector, right? So we are plotting the weight vector here. This is used to scale the graph. So actually, I'm setting the limits, but indirectly it scales the graph. So that is what we are doing here. And just to comment these also, we are using the we are plotting the axis. We are plotting the data points. Okay, this is what we are doing. Each step in the process.
So for sixth line, you can count. I mean, 7th line. Sorry.
Right. So 7th line we need, right? We are using that to plot the decision boundary.
No, linspace minus 15. 15 is the actually the y-axis and x-axis range. No, decision boundary range.
Yeah, we need that for the decision boundary. Yeah. So what I can do is I can make this go here so that the whole thing. Yeah, so I can delete this. Right? This kind of confused. Yeah. So this is what we have done so far. Now, what more we need to plot? The supporting hyperplane, right? So let us add that supporting. Okay, it's the same thing. Only thing that gets added is, so what will get added? If you have to plot the supporting hyperplane, so what should be? Should you change the x value or should you change the y value in the plot?
Y value.
Okay, how will you change the y value? By what should I change it?
You can write the equation and then find the y value.
Okay, so the equation is what? W naught x plus W1 is x1, right? W naught x1 plus W1 x2 is equal to
1.
It's equal to 1, right? So I want x2 in terms of x1. It will be what? X2
1
in terms
minus, of 1 minus W naught to x1 divided by W1.
Okay, this will be 1 minus W naught into x1 divided by W1. Okay. Now I'm just going to write this separately as 1 by W of 1 minus W naught by W1 x1. Is that okay? Is that okay with everyone? What we have done here?
Yes.
Yeah, all that I'm going to do is I need to add this here. That is already there. that minus W0 by W1 X1 is already there. Okay, that is what this is. Minus W0 by W1 XTB is there. Only thing is this is missing. Okay, we add that here. Okay, so this becomes the first supporting hyperplane. Let's first make sure that we get this right. Okay, so this is there, but this is, let's change the line style to dotted, right? I don't want it, I want only my decision boundary to be solid. Okay, so that's fine. Now let's plot the second decision boundary, second supporting hyperplane. What change do I need to make? I want to plot the second supporting hyperplane.
Equal to -1.
Okay, this is equal to -1. So what all things will change?
Multiply by -1 the whole thing above.
Okay, this will become -1. This will become -1, right? Nothing else will change, right? Only this. This is the only thing which changes. Okay, so instead of 1 by W1, I'll now have -1 by W1. Is that fine? So these are the two supporting hyperplanes. Okay, so when you're writing code like this where there are multiple arguments, one thing that I usually do, or it's a good practice, is to move things to the next line. The logical way to move this is the important parameters go in the first line, right? The indispensable ones are the X values and the Y values. The color is kind of something extra, right? So you move them to the next line just so that it becomes a little more readable. So, okay, so this kind of, it's the same code as before, only the thing is that this is more readable than the previous one. Right, so that's the whole plot. So can you observe anything from this graph that you see here? What do you observe?
Support vectors are like lying
on the supporting hyperplanes, right? So that's correct. So let's go back to support vectors. What were they? They were 2, 5, 1, 2, right? So look at this. This is 2, right? Somewhere here is 2. So 2, 5 is this point. 1, 2 is something here. There should be something around -3, -8. So let's see if there's a point like that. -3, -8, right? There's a point here, and of course there is a 3, 10, right? So 3, 10. It's all the way up there. So one way to add some more detail into this graph is make sure that all the non-support vectors are less prominent compared to the support vectors. Okay, so make the non-support vectors less prominent. One way to do that is to add a parameter called alpha to your scatter plot. Okay, if I make alpha equal to 0.5, let's see what happens if you make alpha 0.5. Notice that the points have become less opaque. Okay, so the higher the value of alpha, greater the opacity. So the more solid they will appear, right? So the lesser alpha becomes, the more transparent they will become, right? Or lesser the intensity of these values. Okay, so let's stick to something like 0.3. Now we have made the other data points, all the data points less transparent, but so now we can go ahead and make only the support vectors more prominent. Okay, so that is the goal now, right? Make the support, these 6 support vectors alone must stand out. So what we are going to do for that is we are going to just create a separate array, right? So this is all those X which are support vectors. Their labels are the following, right? So these are the, so let's print it and see. Okay, so these are the support vectors, and So sorry, this should be y sir. So these are you will get the labels corresponding to these support vectors, and like I did for the initial one, right? I'll give them a color. So can someone tell me what this should be? How do I complete this? If I want to color these support vectors, one is green and -1 is red. How should I? What should I plug in here?
The value of alpha greater than 0.
Okay. Anything that is simpler that I can do?
Y sub equal, I guess.
Okay, so y w equal to 1, right? That's correct. So y sub w equal to 1. So wherever y sub is equal to 1, I make it green. Otherwise, I make it red. Okay, so let's see why all this is useful. I'll go back, and instead of plotting the scatter plot of every single thing, I'll make two scatter plots, one for all the data points, and one for this one. And I'll remove the alpha, right? I want these to be prominent. So plotting the data points, that is the comment for that. Here the comment will be plotting the support vectors. Okay, so let's run the whole thing and see what we get. Okay, so notice that you have these things stand out, right? So this red one, these four green dots, green points, and the red one here, right? So these are the 6 support vectors for the hard margin case. Okay, any questions so far?
Sir, here we are drawing the support vectors on top of the data points, right?
Sorry?
The way you have plotted the figure, there you are plotting the support vectors on top of the data points. I mean, for those support vectors which are like the lying on the hyperplane.
I'm kind of plotting them again.
Yeah.
Okay. Any other questions? If not, we'll move on to the soft margin.
How do you tilt the weight vector and do you really have you really calculated those values, like headwind is 0.3 and tailwind is 0.3, and what is the purpose of them? Are they to tilt the weight vector to down towards the downside, like clockwise or something?
No, so this is just controlling the arrow's dimension, right? So if you change this to say 0.8, 0.8, what happens is the arrow head will become like big. That's all.
Okay.
Okay, so that's the only difference. Okay, so we'll move to hard margin. The hard margin is actually very simple if you have done the soft margin is very simple if you have done the hard margin. So this is what we'll do. You have a different data set here, and the main aim of this is to understand the relationship between the C parameter and the kind of margins that you get. Okay, so this is what we'll do. Now, I'll do this kind of quickly, summarizing. So this will be kind of a summary of what we have done so far. So in case you didn't understand the first half of today's session, I hope this will clear things up a bit. So we are going to redo the whole thing, but we are going to do it in a modular fashion, right? So we are going to write a code that is slightly modular compared to what we wrote before. Okay, so we'll write a function called learn. Okay, learn is a function that will accept the value of C as input. Okay, it will accept the function, the parameter C as hyperparameter C as input, and it will train a soft margin SVM corresponding to that. Okay, so this is what we are going to do. Accept C as input and train a soft margin SVM corresponding to that particular hyperparameter value. Okay, so that's what we'll do. Now we'll go over all the steps that we did earlier. So recall that first thing that we did was to find the capital Y. So Y is np.diag of small y. Okay, once we have Y, what did we do? We defined the objective function. So I'll just write a function within a function. It's not, maybe it may not be really the good approach to take, but here we'll just go ahead with it. So I'll return the negative of this because I'm minimizing this. So that will be alpha transpose Q alpha. Okay, alpha transpose Q alpha minus alpha dot sum. Okay, so this requires a half. So I'll add a half here. ALPHA. So that is one thing. So the Q is something we have not computed. So let's compute Q. Q is what? It's nothing but Y transpose XY. So Y transpose X transpose XY. Okay, so we have done that also. Now, once you have the function, what do you have to do? You have to minimize this function. So optimize dot minimize the objective function's value. Alpha init is something you have to specify, right? So alpha init is what? Alpha init will be np dot zeros of n, right? So again, you notice that this n we have not yet defined. So let's go and do that first. D comma n will be the shape of x, right? X is d cross n. So d comma n will be the shape of x. So that is also done. Only thing pending is we have to specify the bounds. Okay, so what will be the bounds in the case of a hard margin SVM? That's the only thing which changes. What are the bounds for a soft margin SVM?
0 at C, right?
Correct, right? 0 and capital C. So that they are the bounds. So this will optimize the function. It will return the optimal values in the object called res, res for result. From that, we'll extract the argmin, right? So that will be alpha. We'll extract alpha and store it with us. Okay, so once that happens, once we have alpha, what do we need? W star is sigma alpha I star xi ya, which is the same as x y alpha. So W equal to x y alpha, and we can actually find, we can go ahead and return a W. That's what we finally need. Maybe we also need alpha to compute few other things. Okay, so what have we done? We have kind of modularized the whole thing. So we have converted all that we have done earlier into a function, okay, a learn function. So in comes a data set, out comes W and alpha. So essentially what have we done? We have kind of unwrapped this or peeped into this black box to some extent. Okay, we have still not understood how this minimization actually works, right? For that, we need to take up a course in numerical optimization. Okay, so we can't do that at this stage. So we'll have to rest satisfied with this level of granularity. Okay, we can't go further. Those interested can.
Karthik sir,
yeah.
Because you've mentioned it, I have a request. NPTEL has just opened up the courses for the July term. If possible, if you can suggest a good course on optimization, I mean, at least I will want to do it.
Okay, sure. Yeah,
I'll also look through it, but if you can suggest something which you think is good, then we'll go for it.
Sure, yeah. Okay, so this is the whole algorithm, right? Only change is instead of np.infinity, this is C. Okay, this is C. So what we have done so far is the learning part of it. Now we need to plot the decision boundary, right? So we have to redo the whole thing, the entire graph. But instead of writing this down, again, what we are going to do is we are going to modularize the whole stuff. So how do we do that? We are going to convert this also into a function. And I'm going to call it plot decision boundary. So what all things does this need? This needs the value of C. Okay, it needs the value of W. it needs the value of the support vectors. It also needs the value of the y support vectors, right? Once it has all this, it will plot, right? So x and y, we are not changing anywhere. So I'm not passing that as a parameter to this function. Okay, the function needs the c value. In fact, it actually doesn't need the c value exactly, to be very specific, but let's say it needs the c value to make sure that it titles the plot appropriately. So I'm doing this for c equal to this c. Okay, so for that reason, we are passing c. W, it needs to plot the decision boundary, and x sub and y sub, it needs to plot the support vectors. Okay, so we have now two functions. Okay, we have two functions and we have to make 4 plots, one corresponding to each value of c. So two functions, we'll make use of them to make 4 plots. Okay, so can someone know, I hope you have understood this, it's not complex. What we have done is just compressed all of them into pair of functions. So what calls should I make? What calls should I make so that I can plot these 4 things? Can anyone tell me? What function calls should be made so that you can plot these 4 points, these 4 graphs?
You can make a list of C, and then for each C we can learn the parameter and then plot.
Okay, right. So let's do subplots. Yeah, that's correct. Right? We have to do that. So let's take up for C is in 0.01, 0.1, 1 and 10, right? C can take these 4 values. For each of these values of C, first thing is, so are you all aware of this function, this utility called enumerate in Python?
It, I think, returns a list of tuples.
Index and the value.
Right. So yeah, so let me just quickly introduce that. So assume that you have a list, say 1 to, not 1 to 3, say 10, 20, 30, 40. So see, sometimes you just need to pick the elements from the list, right? So for x in L, you will do print of x, right? So usually this is what we do. Okay, or the other way of doing this is for I in range of length of L, you usually do print L of I, right? So these are 2 ways of accessing the elements of a list L, right? Now, sometimes what happens is, for like slightly better readability, what we do is we want both the index and the element. So we'll do for I comma x in enumerate of L. So this is what it will do, right? So it will pick up the index of the element and it will also pick up the corresponding element, right? So do you all get what enumerate of a list does? Okay, it's just slightly different way of writing code, right? Nothing else. So I'm going to use that same logic. So I'm going to use for IND comma C in enumerate this particular list. Okay, I'm going to make 4 subplots, right? 4 subplots, one corresponding to each. So it's going to be PLT dot subplot of 2 comma 2, right? 4 subplots, so 2 cross 2, and I will pass the index into this. Okay, so index will go from 0 to 3, so I want subplots to go from 1 to 4. Okay, so I have now made one subplot ready for plotting a particular thing. Now, here what I'll do, I will learn a soft margin SVM for this value of C. So I will do learn for this value of C, train a soft margin SVM and give me its W1 alpha, right? That's what I'm going to do. So it's going to learn and give me W1 alpha. Okay, now I need to plot the decision boundary using this. So plot db C comma W comma X sub comma Y sub, right? So I'm asking to do all these things. So X support and Y support is what? As we already saw, X of alpha greater than 0, wherever it is greater than 0, that is X sub. Y sub is nothing but where is alpha greater than 0. Okay, so you give all this, hopefully it will give us what we are looking for. Okay, so let me run this and see. Okay, so there should be at least one error, otherwise they have done something good, right? So there should be at least one error. So what is the error? C argument has 6 elements, which is inconsistent with. Okay, so we also need this Y sub color, right? So that is missing. So it's not a correct way to do it, but let me just pass Y sub color also. There are other better ways of doing it, but anyway. So what is Y sub color? Wherever Y is double equal to 1, make it green. Wherever it is not, make it red. Okay, so I am passing Y sub color also. And now see if it works or not. Okay, one more error. Okay, so can someone spot?
So in function also we need to pass the
line number 5.
in the function definition.
Colon.
Okay. Function definition, it's there. There is something else which is missing. Okay. This should be not Y double equal to 1, right? We have to look at Y support, right? We are only coloring this, right? So this has to be Y support and not Y. Okay, right? So that is what has happened. Now it has given us these 4 subplots, right? So do you observe what is happening at the higher level? Any observations that you can make, immediate observations?
Will inversely the margin width is inversely proportional with C.
Correct, right? So as the value of C increases, the margin decreases, right? So as C tends to infinity, margin will be vanishingly small, and it will turn into a hard margin case, right? If the data is linearly separable. If it's not, then you cannot. If it's C equal to infinity, you can't solve the problem, right? So the constraints will not be satisfied for a data set which has outliers, right? So that's the soft margin SVM, the relationship between C and the margin. Okay, any questions in how we actually wrote down these two things, these two functions, and subsequently how we learned 4 different SVMs? Okay, so I'm assuming there are no questions there. So for C equal to 10, study the number of support vectors that the model has. So I'll just maybe take this case alone and where did we learn the support vector? Here, right? So here, this is where we did the whole thing. So I just want to do this for C equal to 10. Just run this. So what do we see alpha is? Okay, so it's just a trivial question. So you can just see what it gives, right? So nothing specific, just a random question. Okay, so that's the end of SVM. That's all I had for SVMs. Any questions so far?
So I have one clarification.
Okay.
In this graph. So what does it mean? What is the practical significance when I am using this hard margin and soft margin? Means when I have to use the hard margin and when I go for a soft margin. Because as I
observe, soft merging means I am allowing more data points inside with merging value, and hard means I'm not allowing. I'm some kind of very strict. What should be the my boundary? So when to use which one?
So typically you never use hard margin, right? So hard margin is like for the linearly separable case, and it's you will seldom encounter a situation where the data set is so perfectly linearly separable. There will always be at least one outlier. So by default, you will be using soft margin SVM. The only thing is the real question you have to ask is what C value to choose and what kernel to choose. Right? Typically, those two are the hyperparameters you will tune for a SVM, right? So it's the choice is actually not between hard margin and soft margin. It's between what hyperparameters to choose for a soft margin SVM on a data set. So the dilemma is usually there and not here.
So for the optimization problem, some mathematical model will perform some execution and give me a C value. I just want to understand key means then we never go for a hard margin. No? We always go for a soft margin, and through hypertuning getting this most fit optimized C value.
Yeah, that's what we do, right? We never go for hard margin. We only go for soft margin SVM. So by default, SVM will be soft margin SVM, right? So you will have a C always associated with it. Right. So there's one more observation. I don't know how many of you made this particular observation. Did you notice the length of the arrows in these 4 plots? Here, I don't know if you're able to see it, but it's a very small black arrow here. Here it's jutting out a bit. Here it's slightly longer, and here it's much longer than the other 3. Do you see why that is the case?
Because the length of the arrow is inversely proportional to the margin.
Right. Yeah, exactly. Right. So the length of the arrow, the norm W, right? So higher the value of longer the arrow, higher the value of norm W, or putting it the other way, bigger the value of norm W, longer the arrow, and bigger the value of norm W, smaller the margin. Right. 1 by norm W is the margin. So if your norm W is like large, or if your arrow is large, then that means that your margin is small. Okay, that is another observation that we can make.
Sir, also out of these 4 support vectors, I think we will prefer the first one, right? Because the width of the hyperplanes are more there.
No, right? So see, the width of the supporting hyperplane is only one parameter. The other thing is the bribe that we have to pay for, right? So that there's a conflict between these two. For example, in this particular graph, in this particular plot, it has a wide margin, but then most of the points are violating the margin, right? You have so many margin violations. So
it is violating, but it is more generalizing, right? I mean, like the points are the test point will be accurately predicted. Test point.
Okay, so with this, I don't think we can make a proper call, right? So see, I would even argue that C equal to 0.1 is also reasonably good. In fact, there are fewer points which violate the margin, right? Or maybe C equal to 1. If you were to ask which one I would choose, I might probably choose C equal to 1, because there is the right trade-off between margin violations and width of the margin. Right? So you have to consider the two. Right? But actual choice of C cannot be done using the training data set. In fact, I have done this because it's a toy problem. The actual choice of C requires you to cross-validate. Right? So you'll have to use either a validation set to cross-validate, or you have to use k-fold cross-validation. So without that, you can't actually decide about the value of exact choice of C. Right? So this is just a demonstration of how the margin changes with the C value, right? So that is the main takeaway from this. Okay, so that's all I had. Maybe I'll just go back to one particular thing that I didn't get time to show the other day. Okay, that is in day 1, NumPy arrays.
So GMM is also pending. GMM.
Right. So we can do that. That also we can do. Now I don't mind doing that. So let me just, so you discussed this, right? I just want to know if you discussed the part about this. Where is it? Did you discuss about the MNIST data set on that day? Can anyone tell me?
MNIST data set is not discussed.
Okay, so I'll just quickly discuss that and
and so one more collab is pending, the 6th collab.
Yeah, the 6th collab is more of optimization, what we saw today. Let me see. Let's see. I'll just cover this part and I'm not able to see that particular. Okay, so yeah, I'll just have to do without that. So let me just
so actually the file you are searching for is in day 2 folder.
Okay, is it in day 2?
Yes, sir. Because the previous file was not containing the MNIST part.
Okay, is this the one? Let me check. Okay, where is it in day 2? Can you tell me the name of that file? Where is? No, I'm sorry, I'm not able to find it.
Sir, the file which is edited by Nitin Kumar Jha, I think.
Okay, can you tell me the name of the file?
NumPy arrays. 5 NumPy arrays. Let me copy the name.
Okay, it's okay actually. I think it's fine. I'll just show you the slides and maybe sometime later we can, because I prepared something and it kind of.
Week 1 programming assignment. It's this.
Yeah. No, this one was slightly different. It's the data set, but then I had wanted to show you something specific. But anyway, so basically, what n-dimensional arrays are. So, right. So.
Where is the assignment? I cannot find any assignment in the Google Drive.
No, not in the Google Drive. So it's in the course drive, right? So yeah, so n-dimensional arrays, you have seen 2 kinds, right? One is a vector and another one is a matrix. Now, we have actually not talked about 3-dimensional arrays, okay, and arrays that have other dimensions. So I'll just quickly give you some use cases for ND arrays, right? So just try to visualize this. So 1-dimensional arrays, as you know, is a feature vector, right? So every data point or every training example is actually a 1-dimensional array. So the shape will give you the number of features involved. Okay, so if you look at any standard data set and you take a single data point, that will be a 1-dimensional array. Now, 2-dimensional array, as you know, is a data matrix, right? D cross n. So D cross n is a 2-dimensional array. Now, when you look at unstructured data, right? Unstructured data in the form of, say, images, right? I'll take the case of images because that's the most interesting example. every data point is actually a 2D array. Okay, every data point is a 2D array. So for example, you could have an image that is 10 pixels, 100 pixels, that has 100 pixels in it, right? 10 by 10, 10 cross 10. Okay, so this grayscale image would be represented as a 2D array. So interesting thing is there are 3-dimensional arrays, and you will very commonly use it when you go to higher courses in this degree, such as deep learning. So you look at what is called an RGB image. Okay, so does anyone know what RGB stands for?
Red, green, and blue.
Yeah, right. That's correct. Red, green, blue. These are 3 color channels. So this is of the same size as a 10 cross 10 images. If you look at it, it will also be 10 cross 10, meaning it will be 10 units wide and 10 units long, so 100 pixels. But then it will have 3 such channels, right? So it's called any color image that you see is actually can be represented as a RGB image. So it means there will be 300 pixel values, okay, where they are stacked layer after layer. So the red channel, the green channel, and the blue channel, when they combine together, they give you the color that you're looking at, right? So any color image can be broken down into an RGB image, and that's in NumPy you will represent it as a 3-dimensional array, 3 cross 10 cross 10.
Sir, it's also a rank 3 tensor, right?
Yes, you can look at it as a tensor object.
Yeah.
Right. So in fact, you will, if those of you have registered for the deep learning workshop where we will be doing PyTorch, so the deep learning instructor Arun will take you through tensors in PyTorch, right? So he will do that. This may be a useful thing before you go there. So can someone tell me what a 4-dimensional NumPy array will look like, or what use case does it have?
Videos.
Exactly, right? Videos. So that's correct, but we'll come to that, right? You are correct. So that's a video. Now, alternatively, you can think of a 4D object as 50 images, right? It's a data set, it's an image data set. Okay, so this is just one data point in my data set that has 50 images. So how do we represent 50 data points in such an image data set? Using a 4D array, right? Where the first dimension stands for the number of data points or the number of images in your data set. 3 stands for the color channel, whether it's red, green, or blue. 10 cross 10 stands for how big the image is, right? Spatially. Okay, now that is 4-dimensional NumPy array, and 5-dimensional NumPy array would be a video. Okay, so a video is what? A video is essentially, if you look at it, it's just a sequence of images. Okay, and these are called frames. So every video that you see is ideally what? A sequence of images, one after the other. So if you have a video that has 50 frames, color video, right? Color video, not a black and white video, color video that has 50 frames, and if there are 100 such videos, you will get a 5-dimensional NumPy array. Okay, so this is as complex as it gets, right? Now, a video data set will have to be represented as this kind of a NumPy array, right? So the reason I brought all this up is NumPy's power is far beyond what we have seen so far. Okay, so it's D cross N is not the end of the world. So D cross N is for tabular data that we see in our course, and there are a lot more things that you can do with NumPy, and that's the real power of n-dimensional arrays, right? So this is one thing I wanted to talk about. Then the other thing is regarding reshape, but I don't have access to the MNIST data set, so I may not really be able to do that now. Okay, so that is.
So just a small clarification, sir.
Yeah.
Since you talked about that D cross N, so in our MLT lectures, we have been talking about D cross N, and say, for example, if D is 100, right? So we used to tell that this is an example of 100 features, right?
Yeah, yeah.
Correct. But even that can be represented in tabular format. So in NPy, it becomes a 2-dimensional data, correct?
2-dimensional array, right? 2-dimensional array.
Array, right?
Yeah.
So it is becoming 2-dimensional array.
Sir, and
Right.
also,
Correct,
sir,
na?
in machine learning, we only deal with one-dimensional things, right? I mean, the machine learning techniques works well with the one-dimensional data, right?
All
So
the tabular data are two-dimensional, na? All the tabular data are two-dimensional.
I'm talking about the features. I mean,
so the
thing that you
classical, see, in our course, we have only looked at some kind of a tabular data structure, right? So T cross N. But
is
there are
is that correct, sir? What I said, that in our course we are talking about D into N, D cross N. 100 features are there, but in NP it will still be treated as two-dimensional array, right?
in NumPy it will be treated as two-dimensional array. Yeah, that is correct. Yeah, so that is one thing. Now, maybe very quickly, if you want, we can do the GMM. If not, we can skip the GMM. It's like it's up to you what you all want.
How much time will it take, sir?
GMM will take only say 5 minutes.
Yeah, then we can try to leave that.
Okay, so I'll just maybe do GMMs and then we'll close. So there was GMM.
And sir, in our MLT course, we are maintaining an Excel file, sir. It will be better if you can upload all the links over there, sir, and these files.
Yeah, we can.
Will it be possible, sir?
These 4 links, right? These 4.
Yeah, these 4 classes links and these files, 6 or 7 files of ability.
Yeah, that can be done. Yeah.
Thank you, sir. Thank you.
Okay, so let's finish off the what is this? We are doing this, right? So we did PCA and then
we started with bivariate data and then we stopped from that day.
Okay, so we have to draw 1000 samples from a Gaussian mixture model that has 3 components with mixture probabilities 0.2, 0.3 and 0.5, right? So I call the mixture probabilities 0.2, 0.3, 0.5, and the means are mu's, right? I'll call them, okay, let me put mu as 0, 5, 10, right? Now the standard deviation is sigma. It's the same for all and it's equal to 1. Okay, so I just have a variable, not an array. So let's make them NumPy arrays just to be safe. Okay, so this is the pi value, the mu value, and the sigma value. So how does the generative process work for a GMM? If you want to sample a data point from a GMM, what do we do? Do you all recall what is done?
First step is expectation and then step is maximization.
Right. So first we sample, rather we pick which component to sample from, right? There are 3 components here. So first choose a component. So if you recall, we used this RNG function, right? This is the random variable generator. So this is a generator. So this I'm going to choose from pi with probability, I'm going to choose from the mixtures, the components 0, 1, 2 with probability pi. Okay, I'm going to choose a component. Okay. Why does it not have choose as a choice and not choose? Okay, sorry, it was choice and not choose. So you pick a, right? In this case, we are picking 2. So if you keep running it, you will see that you end up with different components, right? So first 2 times it came as 0. So for 2 and then it came as 0. If you run it even enough number of times, somewhere you'll have to observe a 1. Okay. Okay, I'm not going to play this game. I assume that 1 will certainly come up. Okay, so this is the first step in GMM. Once you choose a component, what should you do next? In a Gaussian mixture model, what is the next step? Anyone remember?
We will select the pi and mu values according to the component.
Okay, so we will sample a point from the component, right? So we'll sample a point. That's what we do next, right? So there are 3 Gaussians. You first pick a Gaussian, one of these 3, based on this probability 0.2, 0.3, 0.5, then you sample a point. So how do you sample a point? These are all normal, right? So you just take mu of that component, the mean of that component, the sigma of that component, and you get one sample, right? So this is the ith sample, let's say. Okay, this is the ith sample. All that you need to do now is loop through how many ever data points you want to pick. So let's say n is 1000. You just pick n data points, and I store it in a data set X, right? To begin with, X will be of size n. Okay, so X will be of size n, all zeros. It can be anything, but better if they are all zeros. So now if you run this, you have a GMM with you. Okay, you have a GMM with you. Now, how do we know if we have done the right thing? We have to plot it, right? So you have to plot and see, and we'll use a histogram like we did for simple normal distribution. Here you have a mixture of normal distribution. So we'll just plot the histogram using a black edge color with, say, 10 bins, right? See what we get. Okay, so doesn't look so interesting. So let's make it 1,000,000 data points so that you have enough detail. Okay, that's taking some time. Okay, maybe 1,000,000 is a bad idea. We can go with 100,000. Stop this.
So maybe we want to increase the gains.
Right, we'll do that. Yeah, oh, that's a good idea. Maybe that's the problem. You're not getting enough detail. Okay, so let's suppress this output and plot it again. Okay, so that's your GM, right? So you have three Gaussians having means 0, 5, and 10. Okay, they have the same standard deviation. So ideally, that you would expect their heights to be the same, but the mixture proportions are different. So the third component is the most prominent, right? That's why you see this height, the height of this to be much higher than the height of the second one and then the first one. Now, if you make it even, right? So let's say we make it 1 by 3, 1 by 3, 1 by 3, and see what happens. Okay, so we have now given equal importance to all three components, and you end up with like three distributions, or rather, this is the same distribution, but three components that have the same height.
Here, when we looked in line number 9, RNG.choice, 0 represents
the first mixture, right? The first mixture, these three values represent the indices of the mixtures.
Okay.
Okay, so that's what they represent. Now, right. That's so the only thing that I didn't do probably is the contour plot. So we really need to do the contour plot or not. What I can do is I can give you a link to a textbook from which I actually took this contour plot. I'll probably Python Data Science Handbook. It's a very good book. So I recommend all of you to go through this. In fact, if you can, in the next 15 days, those of you who are doing machine learning practices, if you can read the whole thing, it will be great, right? So it's the whole thing is available online, and chapter 3 is going to be pretty useful, is what I feel. Data manipulation with pandas and visualization, whatever we did now, right? All these things will be there. So you can go look at histograms, binning, how it's done, right? So you'll see all that we have done, and several more things will also be added. Okay, so please do give it a try. So what I told, what I missed out is showing you this 3D plotting, and I've actually pulled it up from here only, right? So I just copied things from here and then copied it in my Colab. So nothing new. All that you need to do is go through this and you will get it.
Hello, sir.
Yeah.
Sir, first thing is the material which you upload in the Google Drive, only question is there. The solution you did in the class, it is not present in the material, the Colab files. And second thing is I am still confused where I am going to find the assignments further.
See, assignments, we'll send you a link, right? We'll send you a link and you can.
Okay, through mail.
Yeah, through mail. Yeah.
Okay. It is not in the normal portal, na?
No, not. It will be like the normal portal, but then a different link.
And the programming solution which you done in the session, it is not present in the material. Only question is there.
No, right? It's actually there. If you look at the tiny.cc link and say today, right? You go through what you have. If you open it, you open svm.ipy notebook.
If you can just refresh the page, you will get it.
Right. Yeah, I think you are not refreshing. You have not refreshed it, so that's why it's showing. It's not showing. Right. So if you do it, it will come up.
Can you please open once again? Then I will.
I mean, it's there, right? If you just refresh it, it will come up. It should. It's the same folder. I've edited the file that was there in that folder. Is everyone having the same problem? Are you all able to see the?
No, sir. I'm getting the.
Okay, it's just a matter of refreshing, right? Please refresh and it will be there. Okay, so just a few concluding remarks. All this, right? So this is what I want to close with. Okay, so why is this workshop important, or why is coding with NumPy important? The first reason is that you must not let everything remain a black box. Okay, so what we have been doing the last 4 days is to see what really happens when you try to implement these algorithms, right? So when you go to the machine learning practices course, what is going to happen is that you'll be using sklearn, right? Sklearn is a very powerful tool, right? And the moment you have a powerful tool, what happens is that it will take care of most of the things. For example, if you think about PCA, right? So let me just show you sklearn PCA. What happens? So if you want to reduce the dimension of a data set, this is all you need to do. You need to call PCA and you need to do PCA.fit on X. Okay, and you need to give the number of components. Okay, number of components is how many dimensions you finally want. Okay, so this is a great thing, right? If you look at it from one point of view, this is a great advantage because you can very quickly run your algorithms. But the downside is that this is a black box. Okay, so this is a black box, and when you're learning something new, it's better to put in some effort to open this black box, right? It's important to peep into the box. So that's what I think we have done in the last 4 days, right, including today. Sometimes what happens is it's necessary to build your own box, meaning you'll have to build these algorithms from scratch. Okay, so for example, in PCA, that's what we did, right? We tried to build out the covariance matrix ourselves. And then, of course, the eigenvalues and eigenvectors, we didn't compute it by hand. We let the machine do it. So there is also a caveat here. Okay, so we must know when to stop. So in this learning process, when you start with a black box, and when you start uncovering it, when you start seeing how things work inside, you must know when to stop. So, for example, here, this stops with the model level, right? All that you see is a model. You don't know what happens inside the model. So you could ask a valid question. Okay, so I prefer NumPy over sklearn because it helps me understand what is actually happening inside the model. Okay, so that is one level of abstraction. I'm removing it and I'm going down. You could be a little more optimistic and very ambitious, and what you can do is, no, I don't want NumPy, right? I want to know how NumPy works. You could ask that question. It's a valid question. So you could say, you know, how does NumPy calculate the eigenvalues if you are given a matrix, right? That's a legitimate question to ask. So you could say, no, I won't learn NumPy, but instead I will go and spend the rest of my life trying to understand how NumPy works. Okay, so that's not a very good call to take. And if you are even more ambitious, you could say this, right? So Python is a very good language, high-level language, but I want absolute control, right? I want to understand something even more powerful than Python. Okay, so I want to go and learn C. And if you keep doing this, you will end up with building your own computer. Okay, so that's where you'll go and end. So that's on a light note, but the moral of the story is in your learning process, right? As you do more and more courses, it's a very important skill to acquire, learning when to stop, okay, learning when to go deep. Okay, you must not get lost in trying to go too deep. At the same time, you must not remain too shallow, right? So if you just learn sklearn.pca and pca.fit, okay, that will not take you anywhere. So you need to know machine learning techniques. Sometimes you need to know machine learning foundations also, okay, but you also need to know when to stop. Okay, so I hope this particular workshop helped you reach some level of understanding about NumPy. All right. Okay. Anything else? That's all I
How
have.
will this is this in any way, this workshop and what we've learned, is it any way connected to MLP?
Okay, so this lies in between MLT and MLP, right? So it's like, I would say this lies in between the two. As I said here, right? So this is what you learn in MLP. I mean, this is one of the things that you will learn, right? How to use sklearn to solve machine learning problems, right? How to learn from data using sklearn. What this workshop will hopefully do is give you a sense of what is happening when you call pca.fit.
Okay.
Okay, so the MLT course along with this workshop will give you an idea what happens when you call this. So let me just quickly go and show you what happens inside sklearn, right? Because that's, so if you click on the source code, okay, so this is where the PCA class is implemented inside sklearn. So if you go ahead and so these are all documentation. The actual code starts way down here, right? The code starts here. So let's see if we can. I mean, it's very tough to understand it, but okay. So do you see what is happening here? So USVT. Does anyone understand or have a guess of what is happening here? USVT. What could these three variables mean? Any guesses?
I think U is the eigenvector.
Right. Okay. Is there anyone who has done ML at this time who can remember what U might mean, what S might mean, what VT might mean? Something somewhere you studied.
Looks like SBD.
That's right. So this is the S is the singular value, U is the left it will contain your left singular vectors, VT will contain your right singular vectors. So this is there in underscore fit, right? Let's go and look. Underscore fit is right here, right? So let's go and see. Okay, so you can see that SVD is there. So where is it actually being called? There is some SVD solver that's here, and okay, so the point I'm trying to make is, see, all these are at the end of the day NumPy arrays, right? So colon. So here you are picking up what? The first n components. You are picking up the first n principal components. That's what you're doing, right? So you have the list of principal components and you're picking the first n of them, and that's what you're returning in some sense, right? So what this NumPy workshop will hopefully do is, for those of you who are interested in going a bit into sklearn and actually trying to understand what happens when you call a particular sklearn function, Okay, at least we'll have some handle of what is happening, right? So please note that internally sklearn uses NumPy. It also uses SciPy. Okay, so there is that's what I have mentioned in this particular slide, right? So NumPy over sklearn, that's what you would need if you want to understand how sklearn works in the first place. Okay, so that's where this particular workshop helps you. It is a bridge between machine learning techniques and machine learning practices course. So yeah. All right. Any other questions? If not, we will close.
What you were trying but not. Go on, please.
So, what you were saying about the MNIST dataset, if you want to cover that, I can share the link of file of week 1.
Right. Yeah. So do
I have shared in the chat box.
Okay. So now might be a bit late. Okay. Where is the file?
Sir, may I ask a quick question?
Yeah.
So this OPP, where my first question is when and how is this going to be held? And second question is, what happens if we can't pass this exam? So will I get another chance in, let's say, after 3 months?
Yes. You will again be able to register for the workshop, and that will work.
So does it mean registration is mandatory for the OPE?
I mean, no. For the OPP, that's not really a must. So you have to submit the assignments, though. You have to submit the assignments again. There is no escaping.
There a timeline for that?
End of May, I think there is.
Which assignments?
There will be a set of assignments that are released on the portal, a new portal. We'll share the link to that, actually.
When will these be released?
Maybe in 2 days' time.
And we will have how much time for that?
About 15 days, right? Till the end of this week.
And
Sorry.
then OPPE then would be how much time later?
That will be quite some time later. I don't know when, but we have not yet decided the dates, actually.
Okay.
See, actually,
whether this OPP is part of any grading process or it is an extension of workshop?
It's an extension of the workshop, but that is the one which is going to fetch you a certificate.
Yeah, certificate part is clear, but it is not a part of overall grading system, right?
That is the only place where the grading works. Comes in.
See, actually, we are gonna have the paradox in like a week or two. So that's why the timeline is a bit important.
No, see, we will also be there for paradox, right? So no one will be working at that time. So you don't need to worry.
Okay, sir.
Right?
Thank you.
Yeah. So I'll just show this. Yeah. Thanks for, I don't know who shared, Sagar or whoever shared this. Thanks for sharing it. I just wanted to show this. So this is the only thing that was probably missing, right? So this is the MNIST data set, right? So popular machine, digits data set, right? So this is a 3-dimensional NumPy array. There are 60,000 images, and each image is of size 28 cross 28. So we can actually visualize what an image looks like, right? So let's take the first image in the data set, okay, and look at it. If you look at its shape, that's actually a 28 by 28 image. So you can actually visualize this as follows. So it's a grayscale image, by the way. What's the shape? Oh, sorry, this is not shape. This is the 0th image, right? Okay, so this is actually a image of a file. So you can actually cycle through this data set and say the 100th image is also the file, maybe 120th image, case a 2, and so on, right? So this is a typical image data set. Now, what I wanted to show earlier was this reshape operation, which actually transforms. So this is the shape, right? This is what? 60,000 cross 28 cross 28. Now, if you want to do classical ML techniques that we have learned in this course, right, you'll have to reshape this as -1 comma 784, which is like 28 times 28, right? So xtrain new, let's call it xtrain new. So if you look at its shape, it'll actually be 60,000 comma 784, and then you can do whatever learning algorithms that you have learned in this course. So D cross N, okay, in this case it's N cross D, but if you consider the transpose and then look at its shape, it will be a typical D cross N data set. And yeah, so thanks for sharing. I just wanted to show that. Right, so that's all we have. So there are no more questions. We can call it a day and close the workshop.
Just one question on what you just showed a little earlier, 60,000 into 700
Yeah.
odd. Now, when you give a data, it's going to be a file, correct?
Correct, yeah.
So how does reshaping actually work? A file is going to have its own set of information.
Right. So so we'll actually import the file as a data frame. Typically, that's what we do, right? So if you have a CSV file, for example, you will.
Right.
Okay. So since we have time and a few more minutes, we can actually think about it this way. So you will actually import pandas as PD, right? You will import pandas, and pandas has something called read CSV, right? If I'm not wrong, this is the syntax. So you will read whatever file there is. So that will give you a data frame, right? Now, one thing you can do is there is a command called toNumPy or whatever, right? So you can convert the CSV file, assuming the CSV file has only 2 columns. Sorry, not 2 columns, D cross N basically, right? So N columns and D rows. Okay, assuming that your CSV file is of that format, then this will give you a D cross N NumPy array. So you'll have to do these 3 steps before you end up with something like this.
One question. Where is the N coming from? Is the CSV file going to have all the images? That's what you were mentioning.
Okay. If you are looking at images, right? Images, it works totally differently, right? So you'll have to read. So there are like, how do we put it? So there'll be a folder of images, right? So typically assume that you have a folder of images. Okay. So you will read each image using a particular library, and then that when you read it itself, it will come in as a NumPy array in some sense.
Okay.
Right. So there is a popular library, you can take a look at it. So it's called OpenCV. This is so reading an image in OpenCV. If you actually look at this, so okay, I'll just show you the code that they use. So you have imported NumPy and you have imported this library called OpenCV. Okay, and this is a PNG image, right? A normal PNG image that is there in your system. So you use this CV2 library to read. IMRead is image read. So you read the image from your disk, and the image itself will be a NumPy array. So this will make sure that you read it in as a NumPy array. Okay, so that's how the transition happens from a bunch of images in a folder to n-dimensional NumPy array. Of course, this is only one image. You can read the entire directory, right? And you can stack so this is why we studied this stack. So did you study this concatenate, column stack and all that in the last 3 days?
Yes, sir.
Yeah, right. So that's what we do. So you read all these images and then keep stacking them one on top of the other. You will end up with a 784 cross 60,000 array.
So since you have brought pandas into picture, so where pandas is fitting, sir, like we covered in NumPy, and then we are saying that, in NLP we'll be talking about sklearn.
Yeah, so pandas, see, there was actually a plan for covering pandas. The MLP, one of the instructors, Swarnim, has actually prepared a very extensive collab for pandas, but I don't think we'll be able to cover that before the course starts, because there are already Swarnim, this instructor, Swarnim, he's the instructor for MLP, right? So he'll already be doing one more workshop. some of you may already have registered for this, right?
That's fair enough. Even if it covers during the course also, when we registers.
Yeah. So something will be covered, I believe, this time. Pandas along those lines.
So pandas will be a part of MLP, sir.
Yeah. In fact, pandas will be more relevant for MLP than NumPy. So,
will you be there for MLP?
Okay. So no. This time no. I won't be a part of the machine learning practices course, but yeah. So anyway, so anything else? If not, we can, I think, call it a day. And
yes. Thank you, sir. Thanks a lot.
Yeah. So am I audible?
Yeah.
So just one question. The drives mentions 4 different days, but the workshop is actually a 3-day workshop. So do we have any other day for it, or is it done?
10 to 13, right? 10, 11, 12, 13. So 4 days. This link here, is this the link you're talking about?
Yeah.
No, this is all we have. Right? Today is the last day.
Okay. Yeah, got it. Thank you, sir.
And so one more thing, the PPT which you showed today is not in the folder. So can you please copy?
Yeah, that I will upload. Yeah, that I will upload.
Thank
you. Okay,
if
thanks.
we are not live, I would like to have just a discussion.
Okay, actually we are live. I don't think we can stop. I can.
The record.
Yeah, I can.
I just needed advice. I mean, it's advisable to take MLP immediately after MLT, right?
Yes, yeah, that is.
Otherwise, I would probably lose all the concepts.
That is right. So you can ask some of the learners here who have done MLP. Is there anyone who has done MLP from the previous term?
Yes, sir, I have done.
Yeah, what do you suggest? Do you think you took it right after MLT, right?
Yes, I took it right after.
Actually, the workshop sort of has me a little worried about to what extent I'll be able to do all this coding. It was not easy. Today's session was not easy.
Yeah,
today's session.
MLP,
yeah. Please go on.
Yeah. So in MLP, we don't do all the coding from scratch. So we'll be using the libraries, right? So I think only the pandas part is important in MLP. That is what I feel. I mean, if you are good with pandas, then you can be able to code.
MLP is quite easy compared to
yes.
MLT.
Okay. Thank you.
Yeah, so it won't be this. I mean, the coding part won't be this stuff, right? It will be more of a mixture of the machine learning concepts that you have learned in MLT, along with, the SKLN aspect. Yeah, exactly. The SKLN aspect. Okay, how do you implement the techniques that you have learned in this course using SKLN? So
techniques
it won't be
more difficult than the implementation part in SKLN.
Right. So this NumPy, what you saw today is not a sample of what is going to come in MLP.
All right.
Okay. Yes. So thanks everyone for joining, and
thanks to all the instructors for a nice workshop.
Thank you, sir.
Thank you.
Thank you so much. Thank you.
Thank you.
Karthik, can I ask one point, maybe off of this?
Yes, yeah. But it's still, we are still streaming, right? So if you don't mind, then
yeah, sure. Yes, off of this. I already sent a message. If you could check that.
Yeah, sure. Yeah.